We begin our discussion of intervals with this exploration having to do with something called a Riemann sum. Here's the general idea. We'd like to find the area under the curve, between the curve and the x-axis, and we'll find out later that the area under the curve has significance in meeting. But for right now, let's just explore the idea of trying to find the area under a curve. Let's take a relatively easy curve, y equals x squared. Let's take a relatively small interval from 0 to 1, and let's explore that. One way to attack this problem would be to say, we are going to break the area down into rectangles. Because we happen to know easily what the area of a rectangle is. So let's say we're going to break this down into rectangles, but we have to determine how tall each rectangle is. So what if we do something like, we'll take this region from 0 to 1, and we're going to break it down into 4 subintervals, making this 1/4, this is x equals 1/2, and this is x equals 3/4. And then we're going to find the area of each of those rectangles. We're going to call this R sub 4, a Riemann sum using the right hand to determine how tall the rectangle is, and we're going to use 4 subintervals to do that. If we look at that first rectangle is 1/4 wide. And how tall is it? Well, I'm determining the height of that rectangle by the height of the curve at the right-hand side of that subinterval, and that we're at x equals 1/4, and the curve is x squared, so 1/4 squared. Let's go into the second rectangle. This width, still 1/4, but now we're at x equals 1/2, so the height of that rectangle is 1/2 squared. Third rectangle, width is still 1/4. The height of the curve is 3/4 squared. And then the last rectangle is still 1/4, but this time x is 1, so 1 squared. So if we try to clean this up, I get 1/4 times 1/16 plus 1/4 times 1/4 plus 1/4 times 3/16 plus 1/4. We've got a common denominator of 64, so I get 1/64. I get 1/4 times 1/4, that's 1/16. But if I want to convert that to 64ths, I'd multiply those 16 by 4. So how about 4/64? And then how about 9/64? And then 1/4, and again, I want to break this into 64ths. That would be 4 times 16 is 64, so 16/64. If I add that up, I get 1 plus 9 is 10. I get 4 plus 16 is 20. I get 30/64. If I reduce that fraction, I get 15/32. And there's my right-hand estimate. You might ask the question, what do you think of that estimate? I think these rectangles go above the curve. So I think whatever my estimate is, it's not exact. And because those rectangles go above the curve, it's too high. I'm going to call this an overestimate. All right. Let's take a look at the left-hand estimate. Again, we still have we're going to break this down into a bunch of rectangles. All right. This first rectangle is going to be really weird, because we're going to use the left-hand side to determine the height of the rectangle. The first rectangle is 1/4 wide. I want to look at the left-hand edge. How far off the x-axis am I there? 0. So I've got 0 squared. My second rectangle, remember this is 1/4, this is 1/2. It's 1/4 wide, 1/2 squared tall. Nope, I'm sorry. I'm using the right-hand estimate. 1/4 wide, and 1/4 tall. And I got my third rectangle, and again, using the right-hand side to determine the height, 1/4 wide and 1/2 square tall. And then my last rectangle is 1/4 wide, 3/4 squared tall. Cleaning this up again, I get 0 plus 16, 1/64 plus I think 1/16 plus 9/64. Again, we have common denominator 64, 4/64 and 9/64, coming out to a total of 14/64, which is 7/32. What do we think about this estimate? None of these rectangles get as high as the curve. They're all leaving a gap there. I'm going to call this an underestimate. Okay. Our last Riemann sum method that we can look at is called the midpoint Riemann. Now, in this case, we got, again, 0 to 1 is our overall interval. This is 1/4, 1/2, and 3/4. But we're going to determine the height of each of these rectangles by the midpoint of the intervals. The midpoint of the intervals. Well, the first rectangle is 1/4 wide. The midpoint of the first interval that runs from 0 to 1/4 is 1/8. The second rectangle is 1/4 wide, and its midpoint is 3/8. So we'll square that to determine the height of that second rectangle. How about the third midpoint is going to be 5/8. Square that. And the last rectangle yields a 7/8 x value. So 7/8 squared is going to be our height. Cleaning that up, this is 1/64, but times 4, it's 1/256. This one's going to be 9/256. This one's going to be 25/256. And the last one is going to be 49/256. So if we add those up, I've got 10. 10 plus 25 is 35. 35 plus 49 is 84/256, which ends up being 42/128, which ends up being 21/64. And again, what do we think about this one? Well, sometimes the rectangle is above the curve. Sometimes it's below the curve. It's hard to say. We know it's an estimate, but I can't really tell whether it's an overestimate or an underestimate. Clearly, the midpoint seems to be the best of the estimate because it's not clearly an over or under. Okay. Now, that's one way to do it, but there's a lot of arithmetic involved there. But here's what we want to first start away. One takeaway, though, is if a curve is increasing, the right-hand estimate is an overestimate, as illustrated in our first one. If the curve is increasing, the left-hand estimate is an underestimate. Let's take those two facts and make sure that we bring them forward into future discussions. Now, can we get better estimates? And the answer is we sure can, because if you increase the number of subintervals, if you increase the number of rectangles, your estimates will get better and better. In fact, the whole notion of the Riemann sum is that if there's an infinite number of rectangles, you go from having an estimate to having the exact area. So, to generalize, if we want to find the area under a curve from x equal a to x equal b, we can try to add up an infinite number of the areas of an infinite number of rectangles. Now, there is some calculator functionality and some notation we could do that basically says, hey, number these different intervals from 1 to n being the number of rectangles. And if we can multiply the height of each rectangle times the width of each rectangle, delta x being the difference between the x values and broken up into n separate pieces, and then we make that number of subintervals go to infinity, we will end up getting the area under the curve. So, moving on, and that is if you wanted to, in fact, maybe we'll do one of these. In fact, let's do the right Riemann sum, and we'll do it on the calculator using this sum. All right. Let's see what we can get. Go to the calculator. I'm going to open a new document. Let's have it have a calculator page. And let's go under the menu. And under the calculus menu, there is a function called the sum. And that looks a lot like the notation we looked at earlier. We could say, I want to start from I equal 1. And let's do 4, because we use 4 subintervals. The function that we did was called the squared function. So I'm going to say, I'm going to square something. And what did I square? I started at a, and I moved delta x, which was b minus a, or in this case, 1 minus 0, and I broke it into 4 subpieces. And that expression, oh, I'm sorry, and I moved delta x each time I iterated. So I was 1, I was 2, I was 3, and I moved along that chain of x values. There's my expression of height. Let me multiply this by the expression of width, and the width is the same as that delta x, 1 minus 0 divided by 4. And if I hit this, it says 1530 seconds, and that should be the same as what we calculated by hand, 1530 seconds when we did the right Riemann sum. Well, you want more subintervals? Well, how about instead of 40, instead of 4, we go to 40 subintervals. Now this will take longer for the calculator to do. 40, but we get a better estimate. Well, why stop at 40? How about we go to, I don't know, 1,000? Oops. Let's do 1,000 subintervals and see how good this estimate gets. Okay, that ends up being 0.333834. We actually do know what the area under that curve is. It is 1/3, and you can see that with 1,000 subintervals, we're getting kind of close. Getting kind of close. Now, how are we going to get the most exact answers? How do we go from changing the number of rectangles to get to that infinite number? Well, we're going to introduce some other things later to help us make that gap, right? Now, this notation using limits as n approaches infinity and the sigma notation, it's kind of kludgy. So one of the founders of calculus, a guy named Leibniz, came up with a better notation. All the problems that we were just working on can be summarized as and we'll call this the integral symbol, as the integral, or the definite integral, as the function x squared varies from 0 to 1. Okay, so that's our notation. Let's take a look at this example and let's see how this plays out. What portion of the xy plane is described as the integral from 1 to 3 for x? Well, I can draw a pair of axes. I can draw the function y equals x. It's like this. I can go from 1, supposed to be a 1, to 3, and this is the area that we're talking about here. All right? Well, what would happen if we try to make an estimate using a left Riemann sum with 4 subintervals? What do we think the approximation of that integral is? Well, let's start by saying our first rectangle, or how we're doing 4 rectangles, so we're going to do 1/2, 2, 3/2, and 3. The first rectangle, whoops, try that again. The first rectangle, if I'm using the left Riemann sum, how wide? It's 1/2 wide. How tall? Well, if this is the curve, y equals x, and x is oh, I'm sorry, I got some wrong numbers here. This should be 3/2. This other one should be 5/2. Okay, if I'm at 3/2, the x value is 3/2, that means I'm 3/2 tall. My second rectangle, how wide? 1/2. How tall? 2. My third rectangle, how wide? 1/2. How tall? 5/2. And last rectangle, how wide? 1/2. How tall? 3. So this ends up being 3/4 plus 2/2 plus 5/4 plus 3/2. You can say, why didn't I just write 1? Because I want to say common denominator of 3 or 4, sorry. So 3/4 plus 4/4 plus 5/4 plus 9/4. And this totals out to, let's see, 10, 18 fourths or 9/2. Now, when I fill up that space with those rectangles, do we think that's a good estimate? No, we think this is an overestimate. Again, it's a left-hand, oh, I screwed that up, didn't I? I surely did. I did not give a left-hand estimate there. I gave a right-hand estimate. The right-hand estimate for this is definitely an overestimate. I meant to do a left-hand estimate, in which case the first rectangle, let me erase this. The first rectangle is 1/2 wide and it's 1 tall. Second rectangle is 1/2 wide and 3/2 tall. The third rectangle is 1/2 wide and 2 tall. And the last rectangle is 1/2 wide and 5/2 tall, which gives us 1/2 plus 3/4 plus 2/2 plus 5/4. Common denominator of 4, so 2/4 plus 3/4 plus 4/4 plus 5/4. 5 plus 5 is 14/4 or 7/2. And again, since this is a left-hand estimate, we call that one an underestimate. You know, we did all that work. Could we not have just found out what that integral is equal to? What shape is that area under the curve? That shape is a trapezoid. And the area of a trapezoid is base 1 plus base 2 over 2 times height. Now, strangely speaking here, the height is this distance between 1 and 2, because here are two parallel sides, and height is always the distance between the two parallel sides. The height is going to be 2. Base 1 is right here, which is 1, and base 2 is 3, the two parallel sides. So 1 plus 3 over 2. These two cancel, and I get 4. Okay, let's put that in context. Wait, 4 is the real answer. 3/2, sorry, 3.5 is our underestimate, yep. And I wrote this as 9.2. I don't know why I did that. That'd be 9 over 2, or 4/2. Yep, 4/2 is an overestimate. All right. So with some geometric shapes, we can find the true value of the integral. Like in this case, hey, what does the curve y equals the square root of 1 minus x squared look like? If you remember that as the upper half of the unit circle, you'd be right. And what would it take to do a right-hand estimate using two subintervals for this particular shape? Well, that right-hand estimate, my first interval is a two subintervals, so my one subinterval goes from -1 to 0. Okay, its width is 1. How tall is it on the right-hand side? It's 1. The second interval, also width of 1, and its height, 0. So my right-hand estimate says that I'm estimating an area of 1 under that curve. But come on, don't we know the area in the upper half of a unit circle? Couldn't we say with all certainty that this curve has half pi r squared, and in this case, the r is 1. So how about pi over 2 is the real value? All right, moving on. Now, we got to watch out for something here. And I put the expression negative area in quotes here, because there's really no such thing as negative area. But the Riemann sum formula sometimes gives negative values. Why? Because if we multiply some functional value, which may be negative, times some width, which is positive, we end up getting negative values out. Now, this means that if we apply the Riemann sum formula to some formula, to some having to do some curve like y is equal to -x, which runs like that. And then we start saying, well, what about the area from 0 to 4? So that'd be 2, that'd be 1, that'd be 3. Well, the algorithm that we're following says, what's the width of the first interval? Well, it's 1. So there's my how wide. How tall? We said, well, what's the functional value on the right-hand side of that interval? And the answer to that is -1. And what about that second subinterval? Width is still 1, and the height, or the functional value there, it's -2. And our third subinterval, still a width of 1, still a functional value of -3. And then our last one, our fourth subinterval, width of 1, functional value of -4. So now I've got -1, -2, -3, -4. I get -10. And that is going to be what we say is the value of that integral. Or at least that's an estimate of that integral. Okay. Remember, each of these was going this way. Okay. Do we know what the real value is of this is? Well, let's see. What shape is it? It's a triangle, so 1/2 base, which is 4, and its height would be this distance here, which is 4, and this line is underneath the curve, so I'm going to put a negative sign out in front of it. Looks to me like we're going to get out of this a -8. Is that right? Well, let's do one more thing on the calculator. Let's find out. Goes underneath the calculator, under menu, under calculus, we're going to find expression says integral. And we can say, hey, I'm going to go from 0 to 4. And I can put the curve that I'm working with in there. Yep, -8. So these integrals and the Riemann sums that they represent can definitely be negative. Now, if we know the area under curves, and we know this thing about this quote unquote negative area, then we can do all kinds of other work. So let's say we know a fact that the integral from 0 to pi of sine of x dx, that's this curve, y equals sine of x, and the area as I go from 0 to pi. Let's say that area itself is exactly 2. Well, can we make conjectures about what it would be if I went from pi to 2 pi? If I imagine that curve going underneath, and if you said, yeah, that integral is going to have the value -2. Oh, that reminds me. Sorry, we're going to go back here. I'm sorry, I forgot to mention this. The value of this integral is definitely never -8. I'm sorry, just remember that they said, what is the actual area? The actual area, because area can't be negative, is 8. The area in that space is really 8. The integral gave us a -8. Sorry, I forgot to mention that. All right, let's go back. What about this one? Well, what about the integral from 0 to 2 pi? Well, here we had a bunch of area netting out to +2. Here, saying, oh, that looks like -2. This ends up being a big old 0. All those positive rectangles and negative rectangles cancel out. How about only if we stop at pi/2 right here? Only looked at that part. Well, we know that sine is symmetric. Is it reasonable to think that that integral will be 1? Sure. Okay. What about 2 plus sine x? Can you imagine that the axis no longer being here is way down here, and that this distance is 2 from beginning to end, and that sine curve is sitting on top? This area here was 2, and this area here has a height of 2 and a width of pi. This area here is 2 pi. I'm ready to call this 2 plus 2 pi for that integral. Can we imagine in number 5 the curve going twice as big? Every single rectangle that we took the area of is now twice as tall. Probably not hard to imagine that this means that the overall area is now twice as big as well. Okay. Getting trickier now. Sine of x minus 2. Meaning we're now talking about a curve that has been shifted. How is it being shifted? It got shifted to the right 2 units. So instead of being where it is now two units over. But now I want to go from 2 to pi plus 2. Still looks like I'm getting only one of those humps from the sine curve. My conjecture is that that's going to be equal to 2. All righty. Next one. Negative pi to positive pi. Oh, looks like I got a positive 2 here. But what about here? Well, again, the Riemann sum will give you negative values if the curve is below the axis. Negative 2 there. My conjecture is that's going to be equal to 0. All right. What about this one? We're going to go to 2 pi, but we're also talking about a function who's got a horizontal stretch of 2. So the curve is now doing one full arch. We've got a little bit better. One full arch as it goes from 0 to 2 pi. I'm probably thinking that that is going to make that area twice as big. That every rectangle now just got twice as wide. Okay, last one. Cosine of x from 0 to pi. Cosine looks like this. Goes pi over 2 and to 0 and to pi. Oh, looks like positive. Then negative. I'm going to go conjecture that that's a big old 0. All right. Tough. Last one. Suppose k is any positive number. Make a conjecture about the curve negative k to positive k. So here's negative k. Here's positive k. Put them in the right place. Okay, so now we're talking about this particular region. Oh, positive area there, negative area there. It looks like 0. What if k went all the way out to pi? Positive area, negative area, still looking like 0. What if I went further? What if k was way out here? And now I've got negative area, quote unquote, negative area here. But I have the same amount of positive area there. I think this integral from negative k to k of sine of x dx is a big fat 0. All right. So here's a seemingly strange question to ask in the middle of all this. Mr. Fedor drives 70 miles an hour for 3 hours. Let me make a map of that. Here's 1, 2, and 3. Here's 70. Make a graph. Here's time. Here's speed. And what do we see? I went 70 miles an hour for 3 hours. Well, look at the area underneath that curve. It's a rectangle. The area is 210. But more than it's 210, it's 210 miles. And we get this by multiplying 70 miles per hour and multiplying it by the 3 hours. So unit analysis tells us that it's 70 miles or 210 miles. Takeaway here, area under the curve can represent something. And you're like, well, I could have done this without the area in the curve, but I could have also asked, what if it took me 3 hours to reach 70 miles an hour? Would area under the curve now be helpful for finding out how far I traveled, even though I didn't travel at a constant speed? The answer is yeah. Big takeaway, the area under the curve has meaning and it has units. For example, in our previous example, it represents miles traveled. And the units were in miles. Maybe I should say distance traveled. So we can do areas of the curves for reasons. Now, let's take this and take a look at some data. So the car starts from a stop line and accelerates. Here's some data about the acceleration. What does the area of each of the rectangles represent? And again, we multiply speed times time, we get each rectangle represents distance traveled. Now here's the tough part. What's the units for this? Well, the speed was in miles per hour, but my time is in seconds. So when I multiply these two, I'm going to get miles seconds per hour. Well, that's unfortunate. That's unwieldy. So let's look at the same data, but let's change something. Let's change our speed, not in miles per hour, but rather in feet per second. Because then, if I take feet per second and multiply it by seconds, I get the answer that's in feet. So let's calculate the total distance traveled. Let's use the right-hand estimate first. In the right-hand estimate, and we're going to do this, I guess, with 6 subintervals. So I want you to imagine that we have our first, second, third, fourth, fifth, and sixth. And if we're doing a right-hand estimate, our rectangles look like this. Great. Maybe we'll do that here. So R with 6 subintervals. The first rectangle is 1 second wide and 23 feet per second tall. My second rectangle is 1 second wide and 44 feet per second tall. My third rectangle is 1 wide and 62 feet per second tall. 1 times 76, 1 times 85, and then my last one is 1 times 88. And if I total all those up, 23 plus 44 plus 62 plus 76 plus 85 plus 88. 3 plus 4 is 7, plus 2 is 9, 15, 20, 28. Carry the 2. 4 plus 4 is 8, 14, 21. 21 plus 7 is 21 plus 8 is 29. 29 plus 8 is 37. So I'm going to say my right-hand estimate is that the car traveled about 378 feet. Do I think that's a good estimate? That's okay. Do I think it's an overestimate or an underestimate? Clearly an overestimate, as my rectangles are higher than the curve. Let's do the left-hand estimate. Erase all this work. And now let's talk about the first rectangle. Oops, try that again. First rectangle, second rectangle, third rectangle, too wide, fourth, fifth, and sixth. 1 wide. How tall is the first one? Looking at that 0. It's 0 tall. And then 1 times 23 is 44. 1 times 62 plus 1 times 76 plus 1 times 85. And that last one that's coming off the 85 means that the 88 number isn't going to get used at all. And I could total that all up, but essentially I know what it's going to be. It's going to be 88 less than our previous answer because I added a 0, but I took away an 88. So we're going to call that 290 feet. And there's a left-hand estimate. Okay. Let's talk about the midpoint estimate. Now, you're all tempted probably to say midpoint using 6 subintervals. But in the first subinterval that runs from 0 seconds to 1 second, I don't know how fast I'm going in half a second. It's not in my data table, and I can't make it up. So instead of doing midpoint 6 and midpoint 3, my first subinterval is going to be 2 seconds wide, and I'm going to use the value at the midpoint, the value at 1, as the height of that curve. So 2 times 23. My second rectangle, 2 wide, and again, I'm going to use that midpoint. So what's going on at 3? 2 times 62. And my third subinterval is that midpoint plus 2 times 85. Now, you might be saying to yourself, yeah, it looks like we threw away half the data. And I'd say, yep, sure looks like we did. But remember, on this first subinterval, it's over a little bit here, it's under a little bit there. It seems like it's going to wash out. And if I do that, I get 46 plus 124 plus 170. 6 plus 4 is 0, carry the 1. 5 plus 2 is 7, plus another 7 is a 4, carry the 1, 340. And we're not surprised that the midpoint is a number between those two other estimates. Which do you think is the best estimate? I would go with the midpoint. Again, because we know it's not over and we know it's not under. Sorry, we don't know that it's definitely over. We don't know that it's definitely under. Seems like a good estimate to me. And there we go.